Hi everyone, let's transition our discussion away from acids and on to bases, so commonly thought of as the opposite of acids. One of the things you'll notice about all of the items on your screen is that they are in general pretty slippery, so that is typically a property of bases that we know about. Let's look at some other ones. Again, we don't want you tasting anything, but if you did, these bases would taste pretty darn bitter. I'm not sure why you would have ever tasted soap unless you got your mouth washed out by it. Shame on you. But if you have, you're going to see that bitter taste. Acids turned litmus paper red. Bases are going to turn litmus paper blue. Blue for base, so that kind of goes together. That makes sense. As we said, they feel slippery. They will react with all acids to produce salts and water. We said acids react with bases to produce salts and water, so this makes sense that they would do the exact same thing, same products, but now they are the ones reacting with the acid. And bases also conduct electricity, so when bases dissolve, they form ions. One of the most common anions that bases form is the OH minus, or hydroxide anion, and that has a charge, so it can carry electricity, so we would say that it is an electrolyte. Let's get into the two different definitions of bases. So Arrhenius, if you remember back to his acid definition, this one looks pretty darn similar, except instead of hydrogen, his bases are things that produce OH minus, so things that produce hydroxide ions. That means that from Arrhenius's definition, all bases have to have hydroxide. Certainly most of the bases that we'll use will have hydroxide in them, but for an Arrhenius definition, to be accurate for bases, it must have hydroxide in it. Bronsted-Lowry is a little bit different, a little bit more wide-ranging. So Bronsted-Lowry, if you remember, said that an acid was a proton donor, and for him, a base is a proton acceptor. So something that accepts protons as a base. You'll notice it doesn't have to be hydroxide. Hydroxide is really good at this, but if you have anything that accepts a proton, from Bronsted-Lowry's definition, that is a base because it's accepting the protons from an acid. So that gives rise to something called conjugate acid-base pairs. Once an acid and a base reacts, essentially the opposite of an acid is called a conjugate base, and the opposite of a base is called a conjugate acid. So for instance, in this reaction, NH3, if you look at it on the left-hand side, we don't really know whether it's going to behave as an acid or a base until we look at the right-hand side. So NH3 has come over here, and it has become NH4. So NH3 ultimately accepted a proton. Conversely, H2O, let's go blue here, H2O started as H2O, and now it's OH minus. So it has gotten rid of a proton. In other words, it has donated a proton. If you look back to your definitions, things that accept protons, we call those bases. So that means that NH3 is acting as a base here. Things that donate protons, we call those acids. So that means water is acting as an acid here. And that means their opposites are their conjugate base and conjugate acid. So because H2O was an acid to begin with, what it makes is called a conjugate base. And you'll notice OH looks pretty darn basic. It looks like it could accept another proton. So the fact that it looks now like a base makes sense. Conversely, this thing that started as a base, this NH3, we had it as a base. It now has gained a proton. We call this the conjugate acid. And you'll notice that NH4, positive one charge, it looks like it could get rid of a proton, right? It looks like it could donate that proton. So the conjugate acid comes from the conjugate acid comes from the base, and the conjugate base comes from the acid. Now, it turns out that they have different strengths associated with them. So if you have a super, super strong base, hopefully you don't blow out your trunk, but if you have a strong base, that means you're going to form a weak conjugate acid. Vice versa. If you have a really weak base, strong conjugate acid. If you have a really strong acid, you're going to have a weak conjugate base, and vice versa. So if you have a really weak acid, you are going to form a strong conjugate base. One other definition we should have before we move on is something that is called amphoteric. So an amphoteric species is something that can act either as an acid or a base. So it can either donate a proton or it can accept a proton. If you look here at water, water has the capability of either accepting a proton to become H3O+, or donating a proton to become OH-. If you look at H2PO4, H2PO4 could, when it reacts with water, it could donate another one of those hydrogens to become HPO4 2-, right? So it's transferred a hydrogen from the acid over here to the water. If it got rid of that hydrogen, it donated a hydrogen, proton donor, that's an acid, but it could also, conversely, it could be H2PO4 and could become H3PO4. It could accept that hydrogen. And if it accepts a hydrogen, that's a proton acceptor. We call that a base. So here are two amphoteric species, H2O, H2PO4-. We'll keep an eye out for those as we go along. Just like we had strong acids, there are some strong bases. You'll notice that these all have hydroxide in them, that OH-. And one other one to keep in mind, just be aware of, is group 1A metal hydroxide. So that means anything in the first column, for instance, sodium hydroxide is a strong base. Anything that's in that first column of the periodic table, those metals, sodium is one of those metals, combined with hydroxide, they are all going to be strong bases. And you'll notice because group 1A always has a +1 charge, they're always only going to have one hydroxide with them, whereas all of these ones have two hydroxides with them. So that's one way to kind of distinguish between those two. Let's try some practice problems. If you'd like to pause now, feel free, but let's go through and let's identify these acids, bases, conjugate bases. So your job in this reaction is to identify on the left-hand side which one of those is acting as an acid, which one is donating a proton, which one's acting as a base, aka accepting a proton, and then on the right-hand side, you're going to talk about which one is the conjugate acid and which one is the conjugate base. Remember, the conjugate acid comes from the base and the conjugate base comes from the acid. So give that a try. Once you have, here's what we have. Notice the water ended up gaining a proton. So proton gainers or proton acceptors here are called bases. And the thing that comes from a base is called a conjugate acid. Whereas this HNO3, it gave away its hydrogen, it donated it to form this NO3-, so that makes it an acid, and whatever comes from the acid is called the conjugate base. And it kind of makes sense if you think about it. This HNO3 has an H sitting out there in front. It looks like an acid. Acids always start with H. Water could be either one. It's amphoteric. So the fact that HNO3 is acting as the acid is not all that surprising here. Let's try another one. So we have HF reacting with HS-. Again, identify the acid, the base, the conjugate acid, the conjugate base. So once you've done that, let's again look at what's happening. If we look at HF, HF has donated a proton. It's become F-, it's gotten rid of its proton. Things that get rid of their protons, they donate them. We call those acids. They form conjugate bases on the product side. And conversely, this HS-, ended up gaining a proton to get to H2S. When it gains a proton, things that accept protons, we call those bases, and they make their opposites, which are conjugate acids. Let's try breaking that down, not in a whole reaction, but just individual compounds. So let's write the conjugate base for this HClO4. HClO4 turning into a conjugate base, right? If we want a conjugate base, that means we must have this thing act as an acid. If it acts as an acid, what's it going to do? Well, it's going to donate a proton. So you get rid of that proton, H goes away, you're left with ClO4. But you didn't just get rid of H, you got rid of H with a +1 charge. So that's why right here there's a -1 charge on the conjugate base, because we've subtracted the charge by 1. That means we have a -1 charge. Let's try the conjugate base for pH4 positive. If we want a conjugate base, we need this thing to act as, again, an acid. What do acids do? They donate protons. Donate a proton, get rid of it, the +1 and the H went away, you're left with pH3 as your conjugate base. Let's write the conjugate base for HCO3-1. Again, if we're looking for a conjugate base, this HCO3 needs to behave as an acid. What do acids do? They give away protons. So once it gives away this H and a +1 charge, not only is the H gone, you'll notice we also had to bring the charge down by 1. So when we did that reduction, we got to a -2 charge. And you'll hopefully recognize carbonate as your polyatomic ion. Now let's write the conjugate acid. If we're going to write a conjugate acid, we better have these things behaving as bases. What do bases do? Well, bases are things that accept protons. So if HCO3 minus accepts a proton, we're going to have a second H. And that minus 1, remember we didn't just add H, we added H with a +1 charge. Minus 1, +1 come together, neutral charge. That's why there's nothing right there. Let's write the conjugate acid for CN minus. Again, conjugate acid, that means this guy needs to behave as a base. If it behaves as a base, it accepts a proton, so it'll become HCN because we've gotten +1, which gets rid of the negative, and the H on the front side. Let's write the conjugate acid for SO4 minus 2. If we have SO4 minus 2, it needs to behave as a base. It needs to accept a proton. When it does so, it becomes HSO4, and the minus 2 becomes simply -1 because we've taken one H and one +1 charge. Let's also identify the amphoteric species in all of those questions, and if you look back at your work, you'll notice that only one of them acted as both an acid and a base, and it was HCO3. So in one case, we had HCO3 act as a base. It accepted a proton. When it did that, it formed H2CO3. And in another case, we had it act as an acid. We had it lose that proton or donate that proton, and when it did, it became carbonate, CO3 with a 2- charge.